Switching is a fundamental concept in programming that allows us to control the flow of execution within our applications based on varying conditions. Today, we'll dive deeper into advanced topics surrounding switching, focusing particularly on exhaustive switching and its powerful implications in code clarity and safety. So far, we learned about the essential programming concept of switching and its application with enum literals. We explored how enums improve code clarity by providing named values and managing different states effectively. Additionally, we discussed advanced techniques such as exhaustive and labeled switches, inline switches, and using ranges to enhance code organization and readability. The importance of thorough testing to ensure robustness in switch statement implementations was also emphasized. Now, we will cover exhaustive switching in detail and discuss its benefits, coding techniques, and practical uses in various scenarios. Now let's take a look at how we can implement the traffic light enum and utilize a switch statement to control the flow based on its state. We begin by defining the traffic light enum, which includes three named constants: red, yellow, and green. Each of these constants represents a specific state of the traffic light, enhancing the clarity and readability of our code. Next, we set up the main function, where we initialize a variable light with the value traffic light yellow. This variable determines the current state of our traffic light system. We then implement the switch statement that evaluates the light variable. Each case of the switch corresponds to a different state of the traffic light, specifying the appropriate action. If the light is red, the action is to stop. If it is yellow, it prompts prepare to stop. And for green, it indicates go. To ensure we cover all possible scenarios, we include an else equals unreachable clause. This clause acts as a safeguard, triggering a compile time error if an unexpected value is encountered, thus maintaining the reliability and safety of the program. Finally, we print the determined action, demonstrating how the system responds to the current light state effectively. Now let's implement an exhaustive switch statement to handle all possible values of our traffic light enum. In this switch statement, we account for each defined state by providing a corresponding action for each light signal. For the red state, the action is to stop, while the yellow light tells the driver to prepare to stop, and the green light indicates to go. The final clause, else equals unreachable, serves a crucial role. It addresses any potential conditions that fall outside the enumerated types. If an unexpected value were to reach this point, it would trigger a compile time error, ensuring our program's integrity and protecting against unexpected behavior. Next, we will update our enum to introduce a new state, flashing, which requires us to revisit our switch statement to handle this additional scenario. By explicitly defining the action for flashing, which might be to yield, we make it clear that every state is addressed, thus reinforcing code clarity and maintainability. This practice encapsulates the essence of exhaustive switching, establishing a robust control flow in our traffic light system. Now let's take a look at how we can implement user role management using enums and exhaustive switching in our application. We define an enum called user role that categorizes different roles such as admin, user, and guest. This structured representation not only enhances code clarity, but also clarifies the relationships between different roles. Next, we implement a main function, where we initialize a variable role to represent the current user's role, in this case, guest. To determine the access permissions associated with this role, we utilize an exhaustive switch statement. Each case handles a specific role, providing the corresponding permission string: full access for admin, limited access for user, and read-only access for guest. The key feature here is the use of the else equals unreachable clause, which acts as a safeguard. If a new role is introduced in the future, the compiler will alert the developer to handle it, ensuring that all scenarios are addressed. Finally, the permissions are printed to the console, providing a straightforward output of the user's access rights, effectively demonstrating the utility and safety provided by exhaustive switching. Now let's implement a system that utilizes labeled switches alongside exhaustive switching to handle user roles in an application context. In this example, we define an enumeration called user role, which includes three roles: admin, user, and guest. These roles will dictate the access level within the application. Next, we set up a labeled switch statement called action, where we evaluate the current user role. Each case in the switch corresponds to a specific role. For the admin and user roles, we print a message confirming access and use the continue keyword. This allows us to revisit the action switch in case we need to handle further navigation options. Conversely, for the guest role, we print a message and use break, indicating that no further navigation is needed. The inclusion of the else equals unreachable clause serves as a safeguard, ensuring all possible cases are accounted for, thereby reinforcing the principle of exhaustive switching. By seamlessly integrating labeled switches, we establish a clearer and more organized flow of logic in our application, enhancing both readability and control. Now let's see how we can implement a test case to validate user role permissions effectively. In this code, we define a structured type, test cases, which holds each role from the user role enum alongside their expected permissions. By using a slice of structs, we can easily iterate through this collection, facilitating a clear and organized way to test each scenario. Next, we loop through each test case, employing a switch statement to determine the correct permissions based on the user role. Each case within the switch explicitly matches a specific role, yielding a corresponding access level. The inclusion of the else equals unreachable clause is vital, as it acts as a safety mechanism, ensuring that we cover all enum possibilities and prompt compile time errors if new roles are added without corresponding tests. Finally, we utilize an assertion to confirm that the outcome generated by the switch matches the expected result. By adopting this approach, we not only enhance the clarity of our tests but also encourage a proactive testing culture, minimizing the risk of future bugs and solidifying the robustness of our application. As we wrap up our discussion on exhaustive switching, keep in mind that code clarity, maintainability, and safety are paramount. The techniques we've explored today will undoubtedly enhance your programming skills and quality of output. Enums allow for a structured and understandable representation of values, while exhaustive switches secure your code against unwanted scenarios and drive more efficient tests. In conclusion, as you move forward in your journey of software development, embrace exhaustive switching not merely as a technique, but as a cornerstone of clean, reliable, and maintainable codebases. Thanks for joining me in this exploration, and as always, happy coding.